Swayam Prabha. Digital India. Educated India.
Good afternoon, friends. So far we have completed few experiments, in fact a briefing for few experiments, and we have tried to show you how the experiments are conducted, how to analyze their data using my research scholar here. I wish that you find some time and come to Flight Lab and physically do this course. Before we end this module, we have added something extra, and that is related to field of parameter estimation from flight data. It's also a part of an experiment. What do you mean is, what I'm going to explain you is a parameter estimation using flight data. What do you mean by parameter here? You remember when I express CL as CL alpha into alpha and CL cube into QC by 2 U1 plus CL delta E into delta E. Similarly for CM, wrote CM naught plus CM alpha into alpha plus CM cube into QC by 2U1 plus CM delta E into delta E plus many other terms, depending upon how complex is the flight maneuver and how complex is the aerodynamics associated. Here we are assuming the aerodynamics is linear, so we can express CL and CM using the aerodynamic parameters. Which are aerodynamic parameters? CL alpha, CLQ, CL delta E, CM alpha, CMQ, CM delta E. These are all non-dimensional aerodynamic parameters. The question is, can I estimate these parameters through flight test? Is this clear? So that is what I will be explaining you the philosophy behind it, and my research scholar will participate and give you live examples how they have done, and I will be there with them. But they do it by their own hand. Please understand, they have the real experience. So I have requested them to participate. When I say I want to estimate CL alpha, CLQ or CL delta E, there could be many approaches. Please see what is in our mind. Suppose this is a plane. There is an elevator here, and I give an elevator input to the airplane. That is, I am moving like this, I give elevator up and then again take it back. So it is like I have to excite the airplane in a particular mode of interest. What is the mode here? When I write CL and CM, I am talking about CM is pitching moment, so I want to excite the airplane in this mode, longitudinal mode. How do I excite that? I excite by giving an elevator input, and that is what is depicted here. And I can give different types of elevator input. I can give an elevator input something like this. I just simple impulse, I give it, immediately I take it back. I can give a pulse type input, I hold it and bring it back. I am holding the elevator for 3 degrees for 1 second, again taking it back. I can do it like this. I hold it, then give a negative deflection, again I take it up. So I can give multi-pulse input. Depending upon this input, type of elevator input I am giving, the airplane will generate their own longitudinal dynamics. And the question is, by capturing that dynamics, can I estimate these parameters or not? Of course we can estimate, then what is the method? what is the mathematical method for that, and what are the uncertainties in estimation. That is what we will be doing in few lectures. Let us say we have given particular type of input and we are measuring angle of attack alpha. Let's say it goes like this. I am measuring pitch rate Q. I am measuring AZ, the acceleration. It should be something like this. I can measure what is the pitch angle. I can measure what is the flight path angle. And you know all those instruments which are used to find or measure AZ, alpha, Q, theta, etc. The question is, if I could measure them and generate their time histories through measurement, can I use this information to get these aerodynamic parameters? That is what we talk about parameter estimation using flight data. Right? Before you do the experiment, if somebody asks you how to measure angle of attack, so let us recapitulate how we measure angle of attack. Let's say there is this is a horizontal tail, and let's say it can move about a P1. Right? It can move up and down. Now imagine what will happen if this system is seeing an angle of attack alpha. What will happen to this move? We want to develop a field. See, this is the horizontal tail, and this is the boom. Or let's say I put it like this. Now, if there is an angle of attack like this, what will happen? Because this is statically stable, it will turn into the wind. This whole system will turn into the wind, and here, as it turns, it is actually linked to a rotary potentiometer. So the shaft rotates. As shaft rotates, it develops a voltage, and you can acquire that voltage through a data acquisition platform. And initially, you will do a calibration. This much voltage with this much rotation, so I can correlate the angle of attack with the voltage change. That is how we measure the angle of attack. And if we think of pitch rate, this comes from gyro, sense measuring unit, and theta, we'll get through by integrating gyro signal. The point is, these things are available as an experimentalist through flight test. The point of importance is, what flight data should I generate? Should I give a pulse? Should I give multiple pulse? Should I give an impulse? So how to understand what should I do? For that, first thing you should not forget is, what is the natural frequency of the airplane you are testing? Rough estimate. And suppose the short period frequency is, say, 10 Hertz. Right? So you try to give an input such a way that the excited frequency of the airplane is around 10 Hertz. So that daily longitudinal short period will be really excited. So you have to decide the frequency of giving the input, elevator input, in such a manner that it excites almost the airplane in its longitudinal mode if you are trying to estimate this parameter. Okay. For example, if you have given elevator input, you are holding it for too long, put it up and holding it for too long, what will happen? The airplane, as you are holding the elevator up, the airplane will pitch up like this, right? Then it will go like this. Then it will go like this. So phugoid mode will be excited. The phugoid mode gets excited if you get a flight data which looks like this, which is typically a phugoid, almost angle of attack remaining constant, though there will be some changes. Then naturally, you cannot expect to estimate Cm alpha from those data, because there is no such excitement. It's only going like this. What do you want? For Cm alpha, I want to excite the airplane about its own axis, y-axis, which is not happening predominantly. So, I need to select the elevator input appropriately depending upon which parameter I am going to estimate. Right? This is one of the challenges. Second challenge is mathematical model. What sort of mathematical model you are using to estimate those parameters using flight data? For example, let us say we have assumed this as an aerodynamic model for the airplane. What do? We have mathematical model for the aircraft. So we give delta E and we calculate what will be alpha dot, what will be Q, or what will be alpha and Q from the mathematical model. That means essentially solving longitudinal equation of motion. You know that we have done it in aircraft stability and control. So you are actually solving this, assuming some values for these parameters, initial guess values. And you get some alpha Q, and you get some AZ. This is simulation, theoretical. Okay. Now actually, what you do in the flight testing, you give this delta input to the elevator, the airplane when you are flying, and you measure what are the alpha measured, what is the acceleration measured, what is the Q measured. You actually measure. Then, if your model was correct, if your parameter, initial guess parameters were correct, then this and this, they should match, there should not be any error. Right? But you know that the mathematical model is not perfect, nor your measurements are perfect. So, you follow the process or path of estimation. So what do? We said, I find the error, which is alpha measured minus alpha simulated square, Q measured minus Q simulated square, plus AZ measured, AZ simulated square, right? This error, we try to ask a question, what are the values of this parameter? What are the values of these parameters which will ensure this error is minimum? Right? So what is the implicit assumption here? Assumption is this model, aerodynamic model what we are writing is perfect. Right? So if we are flying at a well-known flight regime, I will not doubt this modeling. It's fairly established model structure. But a question in parameter estimation, what you ask? Assuming this model to be correct, what are the values of, combination of values of these parameters which will minimize this error? And those parameters are estimated parameters for the airplane through flight test. Okay, that is the approach. You will see, we will be giving demonstration using a least square method, right? Then we will try to give you some idea about how to use neural network to estimate these parameters. Right? This section I have put purposefully so that you know what is happening beyond whatever we have taught. I know very well this will not go well because unless you do it yourself, you do not get. But if you are interested in doing some sort of a research or post-graduation, do some research in this area of flight testing or parameter estimation, this should motivate you, start your thinking, make you think, how do I follow the conventional path and as well as unconventional, which is a neural network based methods to estimate these parameters. So my research scholar will take over from me and he will be going forward. We will give some examples and we both collectively have done it. Please hear from the horse's mouth. Okay, thank you very much.